Number one, this is from the first practice test. You want to have a smaller margin of error without losing any confidence. So the margin of error equals Z star, that's the number of standard deviations to attain the level of confidence desired, times the standard error. The standard error equals the square root of P hat Q hat over N of the sample statistic times its complement divided by the sample size, N. Now, as N increases, I'm going to put this in math terms, approaches positive infinity, the standard error approaches 0. And that is, it gets smaller. As N gets bigger, standard error is going to get smaller because N is in the denominator. So, if you don't want to lose confidence, that means Z star is going to stay the same. Then the only other factor that you can modify is the standard error. So the only other way to make the margin of error smaller without losing confidence, without losing any confidence, is to make the standard error smaller, which means N must get bigger. If N gets bigger, the standard error is going to get smaller and the margin of error is going to get smaller. So not only does as N approaches, as N gets bigger, the margin of error gets smaller. Okay, so take a larger sample. Number 2 is the only possible answer for this particular question. Number 2, what is true about a 98% confidence interval for population based on a given sample? We are 98% confident that other sample proportions will be in our interval. Okay, so what does that mean? Now, the confidence interval, here's the meaning of a confidence interval, a particular confidence interval. We are 98% certain that the true population proportion is in the interval, not other sample proportions. Okay? We can be 100% confident that other sample proportions, if there's enough taken, will be in our interval. Okay, but it's not a statement of confidence about other sample proportions. It's a statement of confidence about the population parameter, commonly referred to in our course as P. Okay, 2. There is a 98% chance that our interval contains the population proportion. Okay, now this answer is tricky, okay, because it implies, well, for one thing, the wording is close to the right wording. It does concern the population proportion, and that's what the confidence interval is about. But there isn't any probability about whether the population proportion is in the interval or not. Rather, we are 98% confident. It's not a statement of probability. Either P is in the confidence interval or it is not. It's a disjoint probability. It's either, the probability is either 0 or 1. But it's not the same as the confidence interval, as the level of confidence. So the level of confidence, 98%, is a statement that we are 98% confident, okay, not a statement about probability about P. P is where it is. 3. the interval is wider than a 95% confidence interval would be. Okay, now that's true. The higher level of confidence means a wider confidence interval. The margin of error, as stated above, equals z star times the standard error. The bigger the z star is, that means the more confidence you have, then the bigger the margin of error is going to be, which means the bigger the interval is going to be. Because the confidence interval equals p hat plus or minus the margin of error. So the bigger the z star is, then the bigger the margin of error. Now for 95%, z star equals 1.96. And for 98%, z star equals, and I have to take a little time out here and go look it up. Now here is the table for the t-distribution, critical values, and at the bottom are confidence levels. So here's 95%, 1.96, 90%, 1.645, and here's 98, 2.326. So 98% is 2.326. So consequently, a 98% level of confidence can have a z star of 2.326, I believe, which means that the margin of error will be wider. So it will have a wider interval. So anyway, what's the answer? 3. Now only 3 is true. 1 was false, 2 was false, and 3 is true. So 3 only is the right answer. Okay, number 3. We have a confidence interval based on a sample size of n equals 100. We want to reduce the margin of error that's only 1/4 as large. Okay, now here's the rule. Margin of error, if you want the margin of error divided by A and z star does not change, okay, then n must be multiplied by a squared, okay, which means in this case the margin of error is divided by 4. Therefore, this little triangle means therefore, n must be multiplied by 4 squared, which equals 16n, which n equals 100. So the new sample must be 1600, which is E. E is the right answer. Yeah, let me back up here a minute. Circle these right answers. Take a larger sample. 2 only is B, and 3 only is D. Okay. Okay, a certain population is bimodal. Okay, what does that mean? In case you forgot, probably forgot. It means here's a unimodal distribution. Okay, numbers start small, then the small numbers, small percentage of small numbers, small percentage of large numbers, and then in the middle, the numbers get bigger and then they tail off. So that would be sort of like a normal curve or whatever. Bimodal means you have small numbers and a lot of bigger ones, and they get smaller again, and then they get bigger again, and they get smaller again. Bimodal typically indicates that you got 2 populations in one distribution, like men and women or something like that, that are going to have like heights or weights or something that are going to have two different centers. Okay, but anyway, that's bimodal. Okay, population is bimodal. So we want to estimate its mean, so we will collect a sample. What should be true if we use a large sample rather than a small one? Okay, the bigger the sample, So here's the population distribution, okay, bimodal. The bigger the sample is, the more it's going to represent, the more it's going to reflect the distribution of the sample, not the sampling distribution, but the distribution of the sample itself will be bimodal. So 1 is true. Okay, now also if your sample is big enough, what does that mean? Now here is the sampling distribution. What is that? That's the distribution of the statistic taken from many different samples. Okay, the sampling distribution will be approximately normal. Okay, and that is the sample statistic, in this case the sample mean y bar, will distribute around the population mean mu. Okay, so 2 is true, and that's the central limit theorem, which states that a statistic taken from a representative sample has a normal distribution around the population parameter, whether it's proportions or means. Okay, so number 2 is true. 3, the variability of the sample means will be smaller. So what does that mean? Variability is a function of the standard deviation. Okay. As the standard deviation approaches 0, variability approaches 0. So as standard deviation decreases, variation decreases. Okay, well, the standard deviation for a sampling distribution of means equals standard deviation for y bar for the mean equals sigma divided by the square root of n. So the bigger that n is, then the smaller the standard deviation is going to be, so the smaller the variation is. So as n approaches, gets bigger, as n approaches infinity, it's never going to be infinite, but it gets bigger, variance approaches 0. Okay, so as n increases, the variance decreases. So 3 is true. So the answer to number 4 is E. Okay, 5. Manager of an orchard expects 70% of his apples to exceed the weight requirement for grade A designation. At least how many apples must he sample to be 90% confident? Okay, so we got to come up with a sample size. Now, we want a margin of error of 4%. The margin of error equals Z star, in this case, the level of confidence is 90%, so it's 1.645 is Z star, times the square root of p hat. For p hat, we'll use the expected 70%. We're actually using p, but whatever. Okay, p hat, q hat over n. Okay, so we're given all of these different numbers. In other words, the margin of error we already know is 0.04. Okay, Z star we know, 1.645. That corresponds to 90% confidence. Okay, p hat we know, it's 0.7. Q hat we know, it's 0.3. And n is what we want to find out. So we're going to do some algebra here. So what we're going to do is first we'll divide both sides by 1.645. So 0.04 divided by 1.645 equals the square root of 0.7 times 0.3 over n. Now we're going to square both sides. We want to get rid of the radical. So 0.04 divided by 1.645 equals 0.7 times 0.3 over n. Now, the simplest way to do this, we can cross multiply or whatever. We don't really need to do that. Okay, we can imagine this being multiplied by 1. N is going to equal 0.7 times 0.3 divided by 0.04 divided by, this is squared, okay, 1.645 squared. Now both the numerator and denominator are squared, so you can see this as, you'd either go ahead and put this in your calculator like this, or you can see it as n equals 0.7 times 0.3 times 1.645 squared over 0.04 squared. Let me get out the calculator. I'm going to do it the first way. Drag this over here. So second, oh no, don't let me do that. So n equals 0.7 times 0.3 divided by, now I got to use a parenthesis because I have a complicated denominator, or somewhat complicated. 0.04 divided by, it's not that complicated, 1.645 close parenthesis, and I'm going to square it, and there's my answer. Now I'm going to round up 1, so n is approximately equal to 356. Or I could do it the other way, the way I have it here. It's not as complicated. 0.7 times 0.3 times 1.645 squared divided by 0.04 squared. Okay? And get the same answer. All right, now this has this has no parentheses, which is to its advantage. You just got to make sure that you are multiplying by the you got to take the inverse of this fraction right here. So that 1.645 ends up in the numerator and 0.04 remains down in the denominator. Okay? Either way, you're going to be fine. So the answer is 356 or 355, whichever. Okay, and that is D. Okay. 6. A p-value. Well, you can close your eyes and you can understand, we've been over this so many times. The p-value is the probability of the sample statistic, or in this case it says observed. That's the same as sample. Observed means, it's not the population parameter. The probability of the sample statistic occurring randomly, assuming the truth of the population parameter, which is what you're testing. Okay, the null hypothesis. All right, which is null hypothesis. Okay. So the p-value indicates the probability the null hypothesis is true. Remember, the p-value is about the probability of the sample statistic occurring. All right, so A is false. It's not about the probability of the null hypothesis. B, the probability of the alternative hypothesis. Again, it's not about the hypotheses. It's about the probability of the sample statistic assuming the truth of the null hypothesis. So B is false. C, the probability of the null is true given the observed statistics. Again, it doesn't have anything to do with the hypotheses. It's all about the observed statistic. Okay, now we're getting into, this looks a little better. The probability of the observed statistic, so far so good, given that the null hypothesis is true. That is correct. That's true. Okay, so D is true. Now let's look at E. The probability of the observed statistic or the sample statistic given that the alternative, no, it's about assuming that the null assuming the null hypothesis is what we're assuming to begin with. We're definitely not assuming the alternative hypothesis. So the only thing that's true is D. So it's D. All right. Let me put a circle around D, or I can put D in here because it's a little bit less clear. All right. 7. Since this professor wants to see more than 80% of her students enjoy taking her class, at the end of the term, she takes a random sample of the students from a large class and asks an anonymous survey if students enjoy taking her class. What are the set of hypotheses? Okay. More. The key word here is more. Okay. 80%. Okay. Null hypothesis, alternative hypothesis. Okay. Here we go. First of all, the null hypothesis, that's what this is right here, is always an equals. So A is out. Okay? C is out, not an equals. D is out, not an equals. So A, C, and D are out. Now we got 2 left where P equals 80, 0.8, and E where P equals 0.8. So it could be these, but the alternative hypothesis, more, that means greater than 0.8. E is so out, 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 out. And the right answer is B. Okay. 8. Not wanting to risk poor sales on a new soda flavor. A company decides to run one more taste test on potential customers, this time requiring a higher approval rating than they had for earlier tests. Okay, now we're going to talk about errors. So let's see if we can get this. It's complicated or complex or whatever, but let's see if we can get this straight. Okay, higher approval rating. Now, to make this a little bit easier, let's make some hypotheses for ourselves. Okay, let's say, without having to put symbols or whatever, let's say the null hypothesis, oh, here I'm using symbols, old Coke, good as new Coke. Okay? And then the alternative hypothesis, because that's why we're doing this, is new Coke better. Okay, now, they're giving taste tests to people, and the way I was talking about this, let's suppose the approval rating, let's say it was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know if you ever look at approval rating like on Rotten Tomatoes, or, it's usually 0 for 5. Let's say it's 0 to 10. Okay, so let's say previously they decided that you needed an approval rating of 4 points better or something. That the new had to be 4 points better than the old or something like that. So this is new versus old. Okay, and let's say they said, well, if you say the new is 4 points better than the old on a scale of 0 to 10, then we'll say that you think the Coke is better. Okay, and so then that's a positive result. And if I get enough of those, then I'm going to reject the null hypothesis and I'll accept the alternative, which is that people like the new Coke better. Now, okay, so let's say that's the previous standard. Now I'm going to run another set of taste tests, but now I'm going to require on the new test a level of 9. 9 out of, so you can't just say, you had to say it's on a scale of 0 to 10, is it better or not? You got to rate a 9. So you got to be really, really, really sure, really certain that you really think that the new is better than the old. Okay? So I've raised the standard in terms of people's estimation of how much more they like it, from a 4 to a 9, or from a 3 to a 9, or from a 2 to an 8, or whatever. The point is, I increased the standard. I made it more rigorous. Okay? Now what I've done is I've made it harder to reject the null. Now, what does this do? It decreases the probability of a type 1. In a type 1, reject the null when it is true. So by raising the standards, I make it harder for people to decide that they like the new Coke better, which means I decrease the probability that my test, that my survey, will conclude that people like the new Coke better when they really don't. And that's a type 1 error. They reject the old Coke when in fact they like the old Coke just as much as they like the new Coke and would be crazy to go change Coke or whatever. Okay? All right. So I've decreased the probability of a type 1, but I have increased, this happens at the same time, I've increased the probability of a type 2. Failure to reject the null that is false. So I'm increasing the probability that this test will fail to recognize that people really like the new Coke better, and that I will be sticking with an old product when in fact they would like the new one better and may buy more of it or whatever. Okay. So this higher standard of proof will increase the risk of the type 1 error? No. It decreases the risk of a type 1 error. Okay. It increases the risk of a type 2 error. That is true. Okay. Power. It will not increase power. Power, the ability of a test, of a survey, of whatever, okay, of a hypothesis test to correctly reject the null. Okay? Increasing standards definitely decreases power and increases the risk of type 2 error. Okay, so this is false. Okay, so the only answer to number 7 is B. That's the only correct answer. All right. Number 9. Okay, we talked about this in school. Let's go over this again here. Okay. Suppose a manufacturer testing one of his machines to make sure the machine is producing more than 97% good parts. Okay, so, quick. H sub 0, P equals 0.97. H sub A, okay, testing one of the machines to make sure that the machine is producing. Make sure the machine is producing more. More. P is greater than 0.97. Okay. Test result. P-value, probability of the observed sample statistic, occurring randomly, assuming the null hypothesis, is 0.122. Far above alpha. Alpha is usually 0.05. Okay, this is greater than 0.05. So we would fail to reject the null. Now here, a wonderful thing happens. Unknown to the manufacturer, here God is appearing to us. Okay. They make this movie, Noah. They should make a movie about all the way God appears in statistics problems. That would be a lot more interesting. Unknown to the manufacturer, the machine is actually producing 99% good parts. Okay. All right. So actually, in truth, P, reality, is greater than 0.97. Okay? So what happened? Well, with the p-value of 0.122, we're going to fail to reject the null. But A, we should not have rejected, we should have rejected the null. Okay? We should not have failed to reject the null. So A is false. Why? We should have rejected the null because P, truth, reality, is greater than 0.97. It's 0.99. Okay, B, they correctly reject. Well, we're not going to reject the null when p-value is so much bigger. It's 0.122. That's way bigger than 0.05. Okay, so B is false. C, they reject the null. Well, we're not going to reject the null. We already established that we're not rejecting the null hypothesis. Okay, whether it's correct or incorrect, we're not going to reject it. Okay, because the p-value is too big. Failed to reject the null hypothesis. No. If you can only you can only make a type 1 error if the null hypothesis is true. You can only make a type 1 error if the null hypothesis is true. The null hypothesis is not true. See, God told us it isn't true. Right here. This is God speaking to us. Okay, right here. God tells us right here in this problem that it's really 99%. Okay, so God has told us that it's 99%. So we can't make a type 1 error. You can only make a type 1 error. Only make a type 1 error, T1 error, if P sub 0 does not equal P, the true population. Okay, so we did not make a type 1 error. Okay, so that is false. Finally, E, fail to reject the null hypothesis, making a type 2 error. Okay, type 2 error is when the null hypothesis is false and you fail to reject the null hypothesis. So this is true. Okay, so 9 is E. Okay, 10. Which of the following is true about type 1 and type 2s? Type 1 errors are always worse than type 2s. That depends. That is not true. Okay? A type 2 error would be really bad. If you were, well, anyway, that's not true. It depends on the context. Okay? In fact, 2 is the proof of that 1 is false. The severity of a type 1 and type 2 error depends on the situation being tested. Okay? So 3, in any given situation, the higher risk of type 1 error, the lower the risk of type 2 error. This is always true. So this is false, false, true. They are always inversely related to each other. You increase the risk of a type 1, and then the risk of a type 2 is going to go down. The only way you can lower the risk of both simultaneously is, that's in a given situation, is to change the situation by increase n. That lowers the probability of both. Okay? But that's a different situation. Increase n, and you have a different situation. Okay? So the answer is oh, wait, I'm sorry. The severity, look what I did here. I marked this as false, even though I said it was true. Let me erase all this. Okay. Severity of a type 1 and type 2 error depends on, that is true. And 3 is true. Okay? So, the answer is E, 2 and 3. And that is that for test 1. I'll do test 2 later.